Okay, so it's a pleasure to have Joris Moy, and he's going to tell us about causal inference, a unifying perspective on causal discovery. Go ahead.
Okay, thank you, and thank you for the invitation to speak at this location. So this is joint work with Sarah Magliacane, who is currently at the Informatics Institute in Amsterdam. She was a former postdoc of mine, and Tom Klaassen, who's at Radboud University. Um, so um, I'm not sure exactly what you know or do not know about causal inference, but I will just, I'm not entirely sure what your background is, let's put it like that. So I'll just proceed, and if anything is unclear, please interrupt me for questions. I think the group is small enough for that. Well, perhaps you know that establishing the absence or the presence of causal relations can be quite a tricky business for several different reasons. There could be latent confounding, so latent common causes that explain an observed correlation or dependence, but there could be no direct causal relation. There could be feedback loops, so causal cycles. There could be selection bias, so we may be looking at a subset of the data where data points were selected in some particular way. There could be temporal dependence that we cannot ignore and have to take into account. Last but not least, unlimited experimentation is often simply not possible. So in this work, we propose joint causal inference, and that's a framework for causal modeling and discovery, and it allows one to address these challenges in a flexible way. And the main focus of the framework that it tries to address is this unlimited experimentation. So in the framework, we try to combine kind of an observational approach to causality with partial experimentation. So first about causal modeling. So there are different frameworks for modeling causality, and we used structural causal models for the reason that they allow us to take into account latent confounding and cycles. So I will first discuss structural causal models, give a short introduction to those. So this is kind of an overview of several concepts that I will discuss in the next slides, but for now you don't need to pay attention to it. So let's define structural causal models. This definition it's about 1 century old now, this year. It goes back to Wright, a geneticist who first introduced these ideas, and then they became popular in econometrics, and nowadays by the work of Julia Pearl, these ideas have also reached machine learning and AI communities. And I think nowadays that's the most active community that works with these. So what's a structural causal model? It's also known as a structural equation model, but I prefer the causal because it emphasizes that we are modeling causality. And basically you can think of it as a tuple where we have some spaces, standard measurable spaces for the endogenous variables. The endogenous variables, you can think of some variables within the system that we want to model causally. And we have some exogenous variables as well, and they are assumed to be latent. So these are some kind of variables that reside outside of the system, in the environment of the system, and we suppose we have not observed their values. So we have these two spaces in which these variables live, and they factorize into these Cartesian products. And then basically the heart of the model is a measurable mapping, the causal mechanisms. It describes the causal mechanisms, and it maps a pair of value for the endogenous variables and for the latent exogenous variables to a value for the endogenous variables. And I will say more about how it encodes causality. And then we also need we are doing stochastic modeling, so we want to impose a probability distribution on the exogenous variables. And this is this latent exogenous distribution. Okay, so what does it mean? Well, this is just a mathematical object, so it doesn't have any meaning yet. It becomes interesting when we look at the solutions of this model. And we say that if we have a pair of random variables, x and e, that take values in the right spaces, so the endogenous and the exogenous space, we call it a solution if this random variable e has this distribution, exogenous distribution, specified by the model, and if the random variables satisfy these so-called structural equations. So they are of this form: for every endogenous variable with index I in this index set curly I, we have the equation xi equals fi, the ith component of this mapping f in the model. Yeah, with if we give it as input our random variables, and these should hold almost surely. And we can think about these equations. Well, they always are of this particular form. So on the left-hand side, we have the endogenous variable, and on the right-hand side, we have some function of all the variables. And all these functions together specify the causal mechanism that we are modeling. Perhaps it's time for an example to make it a bit more concrete. So formally, you would specify the model by specifying all these elements of the tuple. So I did here. Informally, we typically specify it as follows. We say that we have some exogenous variables here, E1 to E4. They have some distributions. Oh, I forgot to emphasize, by the way, that we assume all these latent exogenous variables to be independent. So this is not just some joint probability distribution on them, but it factorizes. Right, so we can specify for these 4 exogenous variables their distributions, and then we have in this case 5 endogenous variables, x1 to x5, and for those we have to specify we have to give the structural equations. So we have to fill in the right-hand sides with some functions, and note that here the functions or the components of this function, they don't necessarily depend on all the variables. So here, for example, f1 only depends on e1, f2 depends on e1, e2, e3, x3 depends on x1, x2, x5, e3, etc. And these dependencies you can think of as expressing qualitatively the causal relations between the variables. And you can draw a graph for this that you can associate to this model. This is this augmented graph here, and the nodes are the variables, exogenous variables. They are latent, so I dashed them, and the observed variables, the endogenous ones, x1 to x5, and we have arrows between them corresponding to the functional dependencies in the structure equations. So, for example, x1 depends on e1, so we get an arrow pointing from e1 to x1. And x3 depends on x1, x2, and x5, so we get incoming arrows from x1, x2, x5 to x3, and also from e3. And it's kind of funny, x4 depends on itself here, so we get this kind of self-loop.
Can I ask a question, Joris? I mean,
Sure.
This is a naive question here. I mean, this is great. This is, of course, a directed graph. But when you say it's a function, I mean, doesn't that imply that reciprocal relations are also implied, that E1 is a function of x2? So this is
Not necessarily. For example, if x1 is the square of E1, so take the square as a function, then E1 is not a unique function of x1, right? So you can take the positive or the negative root, square root. So it's not equivalent to E1 being a function of x1.
okay. Okay, that's something which is not entirely clear to me, but okay, I'll buy that for now. Right. Okay.
And excuse me, if I could also ask one question.
Sure.
What is the difference between formally and informally? Actually, when it will be different, formally from informally?
Well, I mean, the formal definition was meant to give you kind of the template, and the informal definition is an example, mostly. In practice, we usually write something like this, even though the variables are formally not part of the model, right? So informally we specify
So this is a kind of
distributions
interpretation of a formal model.
Yeah. So the formal model. So if we in the informal specification, we also or we write the elements of the formal model, but we directly already write it in terms of a solution, which are these random variables E1, E2, E3, E4. And formally, we want to separate the model from its solutions for reasons that become clearer in a few slides.
Thanks.
Can I also ask a question?
Yes.
Maybe first a remark. We don't see your cursor. I don't know if you have a cursor or if you are thinking you are showing a cursor.
I was hoping you saw it, but I didn't count on it. But thanks for letting me know.
And so secondly, so I understand this model, but these edges, is that like a hypothesis, or is that what we're after, or you just pose those in an example?
It's a model.
Right, but you know that in advance already? So it's known that what are the edges in advance?
Yeah, so the model from if you have the model, then it induces a graph, right? So because if you have these functions specified, so here it's just still an abstract example. I haven't told you which function f1 and f2 and f3, etc. is, just what variables it depends on. And
but for the rest of the story, because now it sounds, I thought now we're okay. So if we know this information, we're done, right? But
yes, so in practice, you often don't have the model.
Right. So this is what we're after in the end.
So think of it like, so this is what we want to find out often in causal discovery.
Yeah.
But first we should kind of agree on how to model causality in the first place, right? For example, suppose, I mean, sometimes we are, in other parts of science, we are using perhaps differential equation models to model something. And then the question could be, what are the parameters of the differential equation that actually pertain to a particular system? But then first we still have to kind of agree about formalism of differential equations, etc. So consider this something like setting up the stage.
Yeah, thanks, man.
And also something that will be helpful to explain what causality means, actually.
Yeah, I wanted to ask you, how do you read the causal relations from these things?
Yeah, that's on the next slides.
Okay.
That will be the next.
Can I also ask a question before you move on?
Sure.
So on this graph, when you went from the augmented graph to the graph on the bottom, you marginalized over the E variable, because I saw that you have arrows now, for example, between x2 and x3. So what happened?
Exactly. So that's where I was left. to explain these things. So at the top we have this augmented graph where we represented all the variables, but in practice we often, well, since we often don't know the latent variables, it makes sense to go to a kind of a higher abstraction level. So indeed we marginalize, you can think about this as marginalizing out the latent variables and keeping only the observed ones, the x's. But the operation that you need for this is, for example, x1 and x2, they share a dependency on e1, right? They're both dependent on e1, and that means that we have to insert a bidirected edge between x1 and x2 in this marginal graph at the bottom. And similarly for x2 and x3. But we don't do this for example, for x4, because any of these variables that are not shared between the observed variables, we can forget about those.
So in practice, you observe the variable xi, and you're trying to infer the causal relation between those variables, but you might have some latent variable that you don't know are there, and you're not measuring them, and somehow you're still trying to infer the causal relation that is implied by the existence of these unobserved variables.
Exactly, yes.
But you cannot distinguish from what is created by the latent variable from what is actual causal relation between the xi variables.
Well, you can in some cases, and depending on what you do, especially if you can do experiments and perturb the system, then you can learn things about this. So that's exactly the part that I haven't explained. I call this a causal model, but I haven't explained what it means that it's causal. So the way to define this is via, let's say, the model not only tells you how the distributions of the variables are if you observe them, but also what happens under interventions. Here we'll look at a small subclass of possible interventions. They are kind of ideal in some sense. So these are called perfect interventions. So suppose we take a subset of the endogenous variables. Those are, you can think of as the intervention targets. And we have an appropriate value for these variables, the intervention values. Then we can modify our model to model this intervention. We get an intervened structural causal model that I write as the original model M with the subscript do xi equals xii. And it's mostly the same as the original model, but we change one thing, namely we change the causal mechanism. And in particular, we change the components for the intervened variables, because now the values of these intervened variables are just set to the value xi. And the other causal mechanisms for the non-intervened endogenous variables, they remain the same as before the intervention. So we make quite a local change to the model, forcing some variables to take on some value xi, and the rest of the model stays the same. So this basically, you can think of this perfect intervention as completely overriding the default causal mechanisms that normally determine the values of the intervened variables, and we leave the other causal mechanisms invariant. So here, back to our example. At the top, we have the observational situation before we perturb the system with an intervention. At the bottom, we look at the intervention where we set x3 to the value xi3. So what changes? Well, only this structure equation for x3. It becomes this equation x3 equals xi3. And in the graph, then x3 no longer has any incoming edges, right? Nor any bidirected edges attached to it. So this also changes the graph in a certain way. By the way, perhaps for your intuition, it's helpful to if I already tell you the interpretation of these edges in the graph. It only holds under certain assumptions, but let's just ignore that. You can think about these directed edges as the direct causal relations between these variables, and the bidirected edges as representing some latent confounders, so some latent common cause of both that may cause the two variables to be dependent without being directly causally related. So for example, in the top graph, we see this bidirected edge between x1 and x2. And that means that they can be dependent, x1 and x2. But if we intervene to set x1 to a value, there will be no effect. There will be no change in the distribution of x2. Also, if we intervene on x2, it won't change the distribution of x1. Whereas, for example, intervening on x1, it will lead to a change in the distribution of x3, typically. And x3 and x5, they are part of a feedback loop, a causal cycle. So if we intervene to set x3 to some value, then it will typically change the distribution of x5. Also, if we set x5 to a value and leave the rest of the model untouched, then we will see an effect in the distribution of x3. So we have both a graphical way of representing these causal relations and a more algebraic way in terms of these structural equations on the left. Feedback loops, they're often ignored in the literature, but they probably, I don't need to tell you this particular audience that there's a lot of feedback in the world, and perhaps we shouldn't ignore it. Here is one of my favorite toy examples of a structural causal model that represents a cyclic causal system. So take two masses connected by a spring, and they're suspended from the ceiling by another spring. And let's look at the equilibrium heights Q1 and Q2 as the endogenous variables. Then we would say that Q1 causes Q2, and also Q2 causes Q1. Why? Well, if I intervene and I fix Q1 to a certain height, for example, by pushing down the upper mass, and I wait until equilibrium is restored, then Q2 will be at another position than it was originally. And vice versa, if I would pull down the lower mass, it would have an effect on the equilibrium position of the upper mass. So that naturally leads to this graph that we see on the bottom here. Q1 causes Q2 and vice versa. And we can actually, if you work out the equations, model this as a cyclic structural causal model, where the structural equations are of the form as I wrote here. Yeah, so since you're physicists mostly, I think, are you mostly physicists? Then I hope that this is intuitively appealing.
But what is L1 and L0, sorry?
Oh, these are the, I didn't explain that. These are the rest lengths of the springs, and K0 and K1 are the spring constants. Yeah. And M1 and M2 the masses, and G is the gravitation constant.
But then, can I ask a question about this?
Sure.
Does that not mean that Q is automatically also a length?
So yes, the Qs are the vertical positions.
So yeah, right.
Yeah.
But this is, I mean, this is not an expression for the oscillator, obviously. So this is not the. So I don't understand this. What is actually written here?
Well, these are the equilibrium heights, right? So if you wait until you get an equilibrium, so suppose there's some damping, so oscillations dampen out. When we wait infinitely long, then then we will find these
But you're saying actually it's a force equilibrium, so you actually equate the forces.
Yes.
Right. Okay. Then I understand. Okay. So
Yes. Yes. So with equilibrium, I mean, assume that there's damping in the system and wait for infinitely long. What will then be the values of Q1 and Q2? And those can be modeled as a structural causal model. And the nice thing is that it's indeed a structural causal model. So if I intervene and set Q2 to the value 5, for example, I would replace, oh, sorry, I tried to mark something, but it doesn't work. I would replace the second equation for Q2, the structural equation for Q2, by Q2 equals 5. And I would keep the structural equation for Q1 the same. And then I can solve the set of equations to find the corresponding equilibrium state of Q1 under that intervention. So in that sense, it is really a structural causal model if I write it in this form. If you just take the differential equations and you would set all the time derivatives and second derivatives, etc., to 0, you also end up with a system of equations that are satisfied at equilibrium, but they are not necessarily causal in the sense that it's not clear how you have to change the equations to model the effect of an intervention. The nice thing about the structural causal model is that the equations are written in this particular form and also tell you how things change. In this case, equilibrium states, how they change under certain interventions.
So do you have a model like this that is simple and but also has exogenous?
Yeah, so you could think about the masses as exogenous latent variables, or the spring constants. Or
okay.
In this case, I didn't draw them in the graph, so I implicitly treat those as exogenous variables.
Okay.
So we could think of an entire ensemble of such systems that vary in terms of spring constants, masses, lengths, etc. But we haven't measured those. They just give some kind of stochastic variation in our observations within this ensemble. And the only things we observe are for each member of the ensemble, the values Q1 and Q2, and we could still model it with a model like this.
Mm-hmm. Mm-hmm.
So Joris, in following up on that, so you said that if you solve the differential equations and you set the forces to 0, you also get these type of equation, but you don't call that a structural model. Why not? The equations are the same, no? You get exactly the same equation. So, well, I didn't understand the distinction.
Well, I don't have a good slide available to explain that, but suppose we look at this example here. Then if you just consider this to be a system of 5 equations, these structural equations, then you can, of course, so if you're only interested in the solutions of these equations, then you can rewrite them in different ways, right? I could add the first equation to the second, for example, or I could, you can start mixing them in all kinds of ways.
Mm-hmm.
And if you start to do that, then you lose the identity of the individual equations, right? So we want to know that in order to intervene on x3, we change the third equation. But if we first completely rewrite them while keeping the same solutions, then we no longer know which equation to change. So to arrive from the dynamical equations at these equilibrium equations in this particular structural form, you have to basically make sure that you don't rewrite them arbitrarily. Right? I mean, now they are written in, for example, Q1 is a function of Q2 and Q2 is a function of Q1 as they are written now. I could also try to solve them. We have 2 equations, 2 unknowns, so I could try to rewrite them as Q1 is a function of all these Ks and Ls and everything, but get rid of the Q2 dependence, and also a second equation for Q2 that I express in terms of everything except for Q1. If I do that, I lose the causal interpretation. So that's basically the point, because then I no longer know how to change it under an intervention. So that's the structural aspect here.
Okay. Clear. Thanks.
Yeah, so usually I don't talk to physicists, so I just state this as a result. But I think for a physicist audience, it would have been good to elaborate a little bit more on the details of how to start from the dynamics and end up at this structural causal model. Well, I think in most structural causal models that you get from studying the equilibrium states of dynamical systems, you might get feedback. But in our usual daily intuition about causality, we often assume acyclicity, or that's at least a lot easier to reason with. So if we say that a structural causal model is acyclic if its graph is acyclic, if there are no cycles. So far we only saw cyclic ones. Well, the whole theory about structural causal models, well, there's a lot of theory that was developed for acyclic structural causal models. And we recently extended this to a broader class of structural causal models that we call simple structural causal models. This particular example is within that class of simple structural causal models, and it means that we have a lot of theory that we can use for reasoning causally with these models, and also estimating these models from data. But I won't go into the precise assumptions here. Yes, so like I said, for acyclic structural causal models or simple structural, yes, for the rest of the talk, I will just focus on acyclic structural causal models. But keep in mind that we can extend everything to simple structural causal models. And for these models, we can indeed interpret the patterns in the graph causally. So directed edge corresponds to a direct causal relation. A chain of directed edges, we call this a directed path. That is just a causal relation, right? It could be an indirect one, mediated via other variables. And the bidirected edge means that there is possible a confounder between I and j. So we call this then also a causal graph. And this interpretation carries over to simple SCMs, but not, unfortunately, to a very general class of SCMs. Okay, now is there anyone in the audience who has heard about d-separation? If so, please say so, and otherwise I will. My guess would be no.
I have.
I have.
I have.
Okay, a few ones have. Good. So so d-separation is a graphical notion. And the precise definition for today doesn't really matter, but so it's a kind of a graphical definition, and that in some cases allows you to say that some subset of nodes A in a graph is d-separated from another subset B by a third subset Z, and that's denoted like this. Well, and the precise definition for now doesn't matter. What is it? But why is it important? It's important because of a very fundamental theorem, the Markov property, here formulated for acyclic structural causal models. If we have a d-separation between three sets of nodes, so A, B, and Z, in the graph of the structural causal model, then this implies something about the distributions of the corresponding variables. Namely, that the corresponding variables are conditionally independent in this way. So variables corresponding to A are independent of B given Z. And that holds in the distribution that the model implies. So basically, by looking at the graph of a structural causal model, we can already conclude that the distribution that is implied by this model contains certain conditional independence relations. And this is basically the building stone of lots of theory in causal reasoning. For example, Pearl's Duke calculus, if you've heard of it, it's really directly a direct consequence of this Markov property. There are adjustment criteria for estimating causal effects that are used, for example, in observational studies in medicine, that also can be shown in terms of this Markov property. So there's a lot of theory that builds on this. How am I doing with the time? I will never reach the end of the slides that I prepared.
You still have some time, yes.
But at some point we have to make a choice. I think what I will be going to talk about. Now there's one. If the converse doesn't necessarily hold. So if you see a conditional independence, it's not necessarily because of a separation in the graph, but generically this can be shown to hold. And if we assume this converse, then we are basically assuming some kind of Occam's razor, that we are assuming that any independence we see in the data or in the distributions must be explained by the causal structure of the underlying system or model. Okay, causal discovery then, now that we have the modeling basics explained, is the question, it's really about the question, if we have some data, what can we say about the causal graph? Now, in medicine, the standards for causal discovery is by randomized controlled trials. So here, the idea is we start with some group of subjects. We randomly divide them into two subgroups. One is a control group and the other is an intervention group. In the intervention group, we perform a certain intervention. For example, we treat them with a certain drug, and then we measure the outcome. In the control group, we do not do this intervention, or perhaps we do a different intervention, treat them with a placebo. And then we can also measure the outcomes. And the idea is that if we see any significant difference in the distribution of the outcomes in both groups, then we can conclude that the treatment caused this outcome. And the main reason why we can conclude this is because we randomized the assignments to the two groups. Right, so you can imagine that, for example, if you would not randomize it, but divide your subjects over the two groups in some specific way, for example, all the males in the intervention group, all the females in the other group, or all the adults in one group, all the children in the other, then if you see a difference in the outcomes, you're not sure whether to attribute it to the treatment or to other differences between the groups. So that's why the randomization is important here. I will skip this. Yes, and we can actually prove within the framework of structural causal models that this idea works. So suppose we have two variables, treatment C and an outcome X. Let's both consider them to be observed and endogenous. Then we can make two assumptions. The first is that the outcome does not cause the treatment. And that's a very reasonable assumption if outcome comes later in time than treatment, right? Except perhaps if you're in a science fiction movie where time travel is possible. The second assumption that outcome and treatment are unconfounded. That basically means that there's no hidden common cause that influences both the treatment assignment and the health outcome. And that's by the randomization, basically.
Yeah, I guess that is whether you randomized enough or there is like a gene that is responsible.
Yes, exactly. So if you use, say, a coin flip to determine the value of C, the treatment assignment, then everyone, I guess, is willing to assume that there's no latent common cause that both influenced the outcome of the coin flip and the health outcome of the subject. Perhaps, I mean, you can think of exceptions. Perhaps if you believe that God influences, that God plays dice or flips coins after all, then perhaps God could act as a confounder. But here we assume that God doesn't. In terms of the graph of the structural causal model, this means that we exclude our background knowledge allows us to exclude directed edge from X to C in the first assumption and the bidirected edge between X and C in the second assumption. Now, that implies...
Can I ask a quick question,
yes.
also in relation to this assumption 2? Is this actually not also related to the famous placebo effect, where just the knowledge that you are being treated is already influencing the outcome? So the randomization is also mean secretization or something like that.
Yes, well, that's not directly related to this randomization assumption, because you can randomize and still you can randomize it, but not have a double-blind study, right? So the patient knows whether he or she got a placebo, but then you're just answering a different kind of causal question, like what is the effect of being assigned a treatment and knowing what treatment you were assigned to on outcome, versus what is the effect of getting a treatment and you don't know what treatment you get on outcome. Okay. And I sometimes wonder myself why in medicine it's usually the double-blind question that they try to answer, because in practice you often know what treatment you get, so isn't that more relevant then?
Yeah,
I'm not sure. Well, I guess it's because they really want to ascribe the treatment to the drug and not to anything else. But I think both questions would be sensible ones to ask. But it's more the randomization that allows us to assume the second assumption. Now, if we see a dependence between treatment assignment and outcome in the data when we pull the data from both groups, right? So that we see, in other words, a difference in the distribution of X between the two groups, then we can conclude that C causes X. So in other words, that directed edge from C to X is in the graph of our model. And we also can conclude that this is actually the causal effect of X on C is what we see when we compare the two groups. The proof is pretty straightforward, because we just draw all the possible causal graphs that we could have for any unknown structural causal model on two variables X and C. We then use our background knowledge, assumptions 1 and 2, to rule out 4 of them, and we end up with 2 possibilities. And then we apply the Markov property. If in the first graph where C and X do not have any edge between them, the Markov property tells us that C and X must be independent in the distribution. So turning this around, if we observe a dependence, then we must be in the second graph with the edge pointing from C to X. So this kind of sketches how you can now do causal discovery within this framework of structural causal models, where we kind of assume that there is some underlying model, but we don't know much about it, except perhaps some kind of properties it satisfies. Interestingly, you don't need to do randomized controlled trials. You can even say something about the causal graph if you have purely observational data. That was kind of an exciting discovery about 20, 30 years ago. The hope is that experiments are no longer necessary. That could be very nice for all kinds of practical considerations. You don't have to set up these randomized controlled trials if you can just observe, let's say, an electronic patient record data. You just gather a lot of data and you can already find out what causes what. But these methods, they only work under fairly strong assumptions and with possibly very large sample sizes. So that's, I guess, the reason that still in practice, people mostly use randomized controlled trials and they want to be sure about causal relations. So the idea here is that we start from some data here on 4 variables, x1 to x4. We do conditional independence tests on these 4 variables. So for example, we might see in the data that there's a strong dependence between x2 and x4, but it disappears once we condition on x3. And there's an independence between x1 and x2, but they become dependent if we condition on x3, etc. Well, actually, under these 4 observations on these 4 variables, you can already limit the possible causal graphs to these 9 graphs that I drew at the right-hand side. And they all have something in common, namely that x3 is a cause of x4, and they are not confounded. So by these 4 statistical relations that we observed in the data on these 4 variables, we arrive at a pretty strong conclusion, namely that x3 is a direct cause of x4. And now note that we did not have to set up any randomized trial. We just used observational data. The disclaimer is that this relies on faithfulness. And in that sense, well, the randomized controlled trial did not rely on faithfulness, but here we rely on faithfulness. So you can think of situations in which it doesn't work, it fails. For example, because some parameters in the model accidentally cancel out. Now, this was just a causal discovery from observational data with 4 variables. This has been generalized, right? Solving this inverse problem, let's say how to go from conditional independencies that you see in the data back to all the possible causal graphs that are compatible by these. There are algorithms that solve this problem. But as you can see, the number of graphs, it's super exponential in the number of variables. So this really becomes a challenging computational problem, and also a challenging statistical problem, because there are just so many possible causal structures that might explain the data. And if you allow for confounders and cycles, it's even worse. So there are constraint-based causal discovery algorithms that kind of take a more greedy approach, and one of them is the FCI algorithm, but I'll not explain that here. So let's see, how is the time? It's almost done. Perhaps so we already had a few questions. Shall I very quickly finish and then there's room for questions, or shall I take 2-3 minutes to say about what we did on real data?
No, but you do have 15 minutes, so.
15?
Yes.
Ah, okay, good. Then how many minutes shall I take for the present to finish? 5 or so, and then 10 for questions?
You can take the whole 15 and then questions.
Ah, okay. Then I will carry on with with local causal discovery. It's kind of in between the 2 extremes I just showed you. So this is just another kind of causal discovery algorithm that has been proposed, and it works with 3 endogenous variables here called I, J, and K. And it also relies on some observed dependencies and the conditional independence in the data, as you can see. And it also relies on some background knowledge, namely that xj and xk do not cause xi. So that is of a similar nature, perhaps, as what we used in the randomized controlled trial, the first assumption. And for example, if we know that xi is an event that happens earlier in time than xj and xk, then we already have this background knowledge, right? So it's a relatively mild form of background knowledge assumption. And here we also don't need randomization, for example. So so this also could apply to, let's say, observational data in a medical setting where doctors treat a patient in some way and then afterwards they observe the outcome. Then if we take for xi the treatment and for xj and xk different outcomes later in time, then this assumption would be satisfied. And the other two, we can just directly test them in the data. And also in this case, we get a strong conclusion, namely that xj causes xk. And that we actually can take the conditional distribution of xk given xj, that gives us also the causal effect. So in this case, you could say that for xj and xk, correlation equals causation. And again, the proof is straightforward in terms of the structural causal model formalism. You can derive that the only possible causal graphs are these three that are compatible with these assumptions, and then they have in common that there's an edge from xj to xk. So here I have an example, but I think I will skip this for now. So we have seen different, so basically this joint causal inference framework that we propose is a general framework where we distinguish system variables and context variables. So in the examples so far, the treatment assignments, you can think of those as context variables. But in some scientific experiments, they have the experimental design is far more complicated than just treatment or placebo. Nowadays, you get kind of these multifactorial designs where you vary all kinds of different things, right? You have a system that you want to measure, so you measure all kinds of variables in the system, but then you start to perturb it in different ways, and you can think of perhaps you do all kinds of different combinations of perturbations. That's when this framework becomes useful. And basically, what we did here is a trick. So, for example, this FCI algorithm, that's a very sophisticated algorithm for causal discovery if you have purely observational data. So if you don't have context, etc. And basically, the trick that we did in this work is that instead of thinking about that we are modeling a system in a certain context, we take a higher perspective and we just consider the context and the system together as kind of a meta system. So we are basically getting observations. Our data consists of observations of both system variables and the context. And so basically we are observing, let's say, a scientist doing some experiments. We not only observe the measured outcomes, but also the interventions that the scientist did. And then we can jointly model this with one large structural causal model. And we can often we often have background assumptions. For example, that the experimenter first decides on which intervention to perform and afterwards measures an outcome. Then we can already conclude that the outcome does not cause the interventions.
Sorry, just one very naive question. I mean, it feels similar that it feels like it's like including exogenous variables.
Yes. So we are basically extending the boundary of what you call a system and what you call the environment is a bit arbitrary in a way, right? It's a modeling choice. So here we choose to extend our system a little bit more, to include parts of the experiments performed on the system.
Yeah, but in the end, it's still the same. It's just you just increase the number. Could I just say you just increase
Exactly.
variables, or?
So, yeah, so that's the point. So what were exogenous variables now become endogenous variables, so we can use our graphical formalism for it, right? We have observations also for C, etc. I mean, just now consider the data that we have, observational data from this meta system. Because then what we can do is we can just apply causal discovery to the data from the meta system and try to and use it to, for example, infer a graph of the type I showed here.
But can I ask a question?
Yes.
Why isn't this only make things more complicated instead of more simple?
Well, because the question of causal discovery has already been studied in a lot of detail when for, let's say, a purely observational setting. If you only use the X variables here, then we know how to do causal discovery. But if you include the C variables, then people thought, oh, now it's a really different problem, because now we have these different contexts and we somehow have to think about how to combine data from different contexts in order to do causal discovery. But if you think about the context variables just as endogenous variables in the observational approach to causal discovery, then you basically already know the answer of how to do causal discovery, even if you have data from multiple contexts. Perhaps do I have a slide here? Yes. So what we do now in JCI, in this joint causal inference framework, if we just pool the data, right? So we throw together all the data from the different contexts where some experimenter has perturbed the system in different ways. We actually have measured the values of these context variables. And then we just, in this pooled data, we run our causal discovery, where now we can also include the context variables. And we can actually, if we have some background knowledge on the relationship between the context and the system, for example, that the system does not in any way causally influence the context, so the decisions on the interventions, then we can actually use that to get a smaller possible set of causal graphs. So if you don't use the background knowledge, then no, it doesn't get more difficult, because we can just use what we used before. If we add these background knowledge assumptions, then yes, we have to adapt the algorithm a little bit, but that's what we did here. So we adapted it to FCI, JCI, for example. And in that sense, you can see that we can now deal with an arbitrary number of context and system variables, whereas before FCI was typically only used without any context variables. So basically, we get this kind of more general algorithm, FCI, JCI, that we can run in many more situations than if we would restrict ourselves to randomized controlled trials or LCD or FCI. Does it work in practice? Yes. So we did some simulations, and making use, or basically exploiting the signal that you see if you perturb the system in various ways by using FCI, JCI, helps you to better estimate the causal relations between the system variables. That's basically the upshot. I think I have to. Yeah, so you see that the precision increases a lot here if you go from 0 context variables to 1, 2, 3, 4 context variables here. So you can here really see that perturbing the system is extremely helpful for understanding it. That's perhaps not very surprising, but here we propose a method in which you can actually take any experimental data sets and discover these causal relations within this framework. Yeah, it's also consistent. We have extended it to cycles, and we have validated it on real-world data. And in the interest of time, I think I will leave it at that. So the conclusion is that, well, often we would like to estimate from data or from experiments causal relations between variables. And I think it's an underexplored topic in statistics and machine learning, though it's of course a very important topic. There are various approaches that have been proposed, and we kind of unified these ideas into one framework that not only recovers the existing approaches, but offers new approaches that are especially interesting if you have more complicated experimental designs. So that's it. Thank you for your attention. And so this was joint work with Sarah Mangiakan and Tom Klaas.
Thanks a lot. Yeah, we have time for some questions. Well, I would definitely would like to see, you know, at least an example where you say you validated this with data.
Yeah, so I think this this example is perhaps best to show what we can do. It's not really a validation because the ground truth was unknown. We also have another example on yeast that is more like a validation. But I think this is, even though it's not really a validation, I think it's nice to illustrate what we can do. So here is certain protein abundance data from where they measured the concentrations of 11 different phosphorylized proteins in human immune system cells. And they did these measurements, well, these are single cell measurements, and they did these in 8 different experimental conditions. The first condition is kind of a baseline condition, and then in the other 7, they added all kinds of reagents to the cells. And basically in this heat map here, you see the measurements for the individual cells. You see that there are differences between these 8 conditions, right? Now the question that you would like to answer here is, given these data, can we estimate the causal relationships between these 11 proteins? And that's what the biologists call a signaling network in this particular case. It was about 3 decades of research to arrive at this consensus network that I showed here. But we can also try with this data to just estimate this network from this one experimental data set here using our FCI-JCI algorithm.
You say consensus because this is what they somehow came up, but they haven't proved it or something. Is that
so? This is, I mean, a consensus in the sense that this is a summary, this consensus network of tens or even hundreds of experiments that found possible causal relations between these variables, between pairs of those, and then they looked into possible regulating mechanisms and molecular mechanisms that would explain these. And then back in 2005, if you read the biological literature, then you would find some kind of evidence for these causal relations that are depicted here. And that's what consensus means. But it's probably not complete because for example, an important feedback loop that is known to be there back from ERC to REF is missing in this consensus network. So it's a partial picture of the ground truth, let's put it like that. Now, if you use only the observational data, so only the first batch here, and you run the FCI algorithm to causal discovery, then what you find is this. you find some dependencies. For example, ref and mec are strongly dependent, but you don't find much in terms of causal relations. But if you use the FCI-JCI algorithm that you can now feed with all the data from the different experimental settings, and you use that the measurements don't affect the experimental setting that was chosen, then you end up with this causal graph that's estimated. And suddenly this looks much more informative. So you see that this system, that this signal that you get from perturbing things, you can use it to estimate causal relations between the system variables, but also you can use it to learn the effects of the interventions that you're doing. So for example, psi-tectoriginin, it is known to be a PIP2 inhibitor. That was already known, but it's also something that our algorithm discovers from this data. So that psi-tectoriginin has a direct effect on PIP2 and doesn't directly affect the other variables. And now I'm not sure exactly which one is more accurate, the version that we learned from the data or this consensus network. So that's now an open question for future research.
But are there differences?
Yeah, there are definitely some differences. They're not the same. So for example, here mec causes ref in our estimate, and here ref causes mec in the consensus network. So that's definitely one difference. But if you look in the data, then actually it makes much more sense to have it from mec to ref than the other way around. But that's kind of a complicated story that involves feedback and perfect adaptation, and that would require, well, I mean, going into those details, that's another topic for another talk, perhaps.
There's a question here by Alexandru.
Yeah, I have comments. One is about this issue of placebo effect. I think it points out to the difficulty of finding the exogenous variables, right? So it's like you're not observing them, and then assuming they are given, well, you can establish causality, but the problem is how to get them, how to come up with them, because they're not observable directly, or in this case, it's even more complicated. In fact, they were observable, but they were not taken into account by the modeling. So before placebo effect was discovered, people did not take into account certain variables.
Mm-hmm.
For instance, the variable of administering the treatment, right?
Mm-hmm.
So if this is done because that's the exogenous variables, like administering the treatment causes the treatment to go, but also may cause, if it's transparent to the subject himself or to the evaluator, it may cause cure. It may cause the effect, independently of the treatment itself. And that was not taken into account, although in practice it was observable. It's not like a hidden variable. But yeah, so it depends on, I mean, yeah, so when trying to establish causality, one has to be, it's like almost like an art. So, and that might pose a problem for machine learning, because, I mean, right? So how does a machine discover the placebo effect, for instance, if the causal model never gave this information? I mean, so to speak, the pre-causal model, the bunch of variables that you're considering for your causal model,
yes,
include that.
Yes.
And the machine learning will not work. At best, it might establish spurious causalities between treatments that don't actually do the effect, the expected effect. So that's one question.
Yes.
I haven't, but maybe later.
Well, maybe I first answer this question. So that's yeah. So a very good question. And okay, maybe perhaps two comments here. The first one is that in this framework, this whole modeling and discovery framework that I spoke about today, we always take for granted that the variables have already been defined or chosen in a good way. Perhaps, well, so the variables that are observed, they should somehow be causally meaningful to start with. Otherwise, we can't do much.
But also the assumption is that no other variables than the ones in the model, like the endogenous plus exogenous, are meaningful.
No. So it could be that there are other variables that we have not observed that would be causally relevant, and the framework is robust to the presence of those. So there could be latent confounders that we don't know about, and we will. For example, here between ref and mec, you can see this in the top left corner. The framework doesn't decide whether the dependence between ref and mec is due to a causal relation between the two, so ref causing mec or mec causing ref, or it could be perhaps a latent confounder that we don't know about. It could be another variable that confounds them. So it doesn't have information to draw a conclusion here, so it doesn't orient this edge. But in the presence of other variables, sometimes under the faithfulness assumption, you can say that, well, there are two possibilities. One is that the dependence is due to a latent confounder, but actually I don't need that assumption. That there could be a latent confounder, but it's kind of unlikely because the parameters would have to be very specifically tuned so that some other independence, some dependence disappears. So it's kind of an unlikely explanation, and the system then prefers the hypothesis that there's no confounding because it's a simpler model. So there's also some kind of model selection here, and that allows us to, in some cases, rule out the influence of these latent possible confounders, even though we don't know, or we make no assumptions that we have measured them.
For instance, let's take the concrete example of the placebo effect. Suppose the variable that causes both, essentially the decision or the administration of the drug, the moment in which this is done or announced to the subject, it's not in the model. It's not one of the variables in the model. Then, all right, so then there is a spurious correlation between a treatment that actually doesn't cause the cure and the cure, the effects, right? Which is apparent in, statistically. Now, probably you could spot this.
But wait, so the placebo, so you're distinguishing the choice of the treatment from.
Yeah, okay, so what I have in mind first, it's, let's explain the placebo effect. Somebody mentioned already, I think it is connected to confounders. So to explain it, you have to add another variable, which is essentially, we can call it the administration of the treatment. Like when you actually, or the decision to give the correct that treatment to the subject. And that is a kind of action that is actually we assume is transparent to the subject. So the subject gets to know instantly, right? That he's being administered this treatment, right? Now, this causes the treatment on one hand. We distinguish the treatment and its administration, because the treatment is when you actually start to treat and you do you get the drug in your body.
Yeah.
All right. So the administration of the treatment, whatever you call it, this decision causes the treatment, but on the other hand, it also causes, due to the placebo effect, essentially, the patient to improve, right? Independently of the treatment, right? So that's a way to put into this model, I would say, the placebo effect as the existence of this confounding variable between the treatment and the treatment that is not causally efficient in itself and the cure, right? Via the common, and of course,
I'm not sure if it's confounding, but okay, I will. Let's go along
both,
with it.
Right? So it is causing both. So the treatment, which by treatment we mean the fact that into the body a certain drug goes periodically for a month, it's caused by the administration of it, like the act of actually giving it, and we assume a kind of giving that it's public, that in the sense of like the subject knows when it's given that treatment, right? Because he's told, whatever. So that's one event. So it causes the drug to get into the body, but it also causes the patient to improve because of the psychological effect of being given the treatment. And these are independent of each other. So that's the confounder, right? But then you can observe, if you neglect it, you see a correlation between the treatment and the improvements, right?
Yes.
And the confounder is this common cause of administering in a transparent way to the subject. So that's one way to put into this model, I would say.
Yes.
It seems to be very simple.
But I guess the question is whether the algorithm will be able to get at the directed graph, or it will be just like the half and mech there on the corner that doesn't.
Well, the first question would be,
but doesn't direct.
Yeah. So my question was, okay, so I know how to model the placebo effect if I know about it, if I know the placebo effect into this modeling. But suppose I haven't yet discovered the placebo, I don't know anything about placebo effect. So my variables that I, as long time people took into account, only the treatment and like that means that the drug itself and the cure, like the effects, right? So then will the model or via interventions on these variables discover that there is a confounded, I mean, even if it doesn't know the confounding variable because it's not in the model, but will it discover that there is the possibility of or not? That's the
So it's this is indeed now that I understand precisely what you're referring to. This is indeed a very subtle aspect that I've also spent quite a while thinking about. The answer, I think, can be found only in making very clear what the variables in your model are about. And it is hidden, it is in this second assumption in the randomized controlled trial, in the following sense. If indeed we have also this other confounding variable, it's also a context variable, but it's latent. I should be able to draw now. That would make the whole discussion easier, but I can't. So it depends on what you call C. If you are clear about the meaning of C, right? So if you don't confuse the treatments, the physical treatment effect with the placebo effect, or the administered treatment from the act of assigning treatments together with communicating to the patient what was treated, you have these two very different variables C. As long as you clearly distinguish them, there can't be any confusion, because in the end you're answering some causal question about the effect of something called C on X.
I agree.
And that's when you have to be careful when you either say, I can draw a conclusion about the actual working of the drug in the body, or the sort of, or instead about what is the effect of having a doctor transparently assign someone a certain treatment. So
I agree, but you see that this assumes that the variable that you're talking about,
exactly,
the doctor,
yes. So someone
already incorporated
exactly.
into the model.
So someone gave me the data, and it's for some of these two variables C, and I just draw a causal conclusion out of the data. But then if I communicate it back to the doctor, we have to be sure we talk about the same variable C.
Right. Which I think it's the difficulty in practice.
Yes, for sure.
One of the difficulties.
Yes. Yes. So you have to be very careful sometimes. Are you talking about in the intended treatment, or actually the actual treatment, or the actual procedure?
Because in reality, there are
very complicated.
Potentially infinitely many variables are out there.
Yes.
That we can even observe some of them, but we are aware diffusely of them, but we don't put all of them in our model. We disregard most of them because we think they don't matter. And in this case, the presence of the doctor in the room that creates the placebo effect was for a long time disregarded. And I mean, if you don't give to the machine will not come up with it somehow.
No,
if you
no,
put it
exactly.
into the model, then it will be able to disconfound them. Right? True.
Yeah.
So that was my remark. Yeah.
Yeah, but that's, yeah, I think that holds for any type of causal discovery, whether it's done by humans or by a machine.
Okay. But there was a question here by Robert, but I don't know if you removed it. Removed the question.
Well, I thought, okay. So I was wondering, so practically, right? So for how many nodes does this work more or less okay?
Well, it depends a bit on how sparse the graph is, but it depends also what you call this. But this FCI JCI algorithm that we proposed here, that can scale up to a few hundred nodes in the graph. And with this these simpler versions, like this LCD algorithm, for example, we have run that on gene expression data from yeast with about 5,000 variables.
And people in medicine, for instance, do they trust this enough to use this, or for reasons that Alexander talked about, they don't? Or
well, it is not so. They are very. They don't know about these methods yet. I can tell you that some of the psychologists at the University of Amsterdam, they are doing it. They are using it for interpreting their interventional psychological data. And in medicine, so I don't trust it well enough myself if we just do this kind of, this kind of application here that I just showed. This one here, I wouldn't trust every edge here myself, but it is nice for generating hypotheses, for example. So the next step could be to look exactly at the differences between this consensus network and what we find here, and kind of do a robustness analysis of what of these parts of these graphs are robust in our findings, and then this suggests possible new causal relations that were yet unknown, and then you can go to a biologist and propose or set up a new experiment to get better evidence for it. But it's always, because it always relies on this faithfulness assumption, it is always less reliable than the randomized controlled trial, which does not rely on faithfulness.
can I ask a last question? What if faithfulness is not true because, for instance, there are logical relations between nodes or semantic relations between nodes?
Well, then
can you do anything there?
These out-of-the-box methods, they will fail, but there's active research on weakening the faithfulness relations in several ways, and kind of making these methods more robust to certain violations of faithfulness. Okay. But if you don't have any kind of faithfulness, then you can never really go beyond saying that, well, it could be a fully connected graph.
No. Okay.
Yeah.
There's one more question here by Clelia. Clelia, do you want to ask?
Sorry, actually, the question is actually almost, it was basically the same question. I was wondering how many variables you can work with and how robust was the results. But actually, maybe I can ask you, how is the algorithm working? Because I mean, I can imagine you cannot go through all the possible combination because you have a super exponential number of possibilities. So I was wondering if you have like some type of PD or Monte Carlo procedure or like a divide and conquer. I mean, how do you deal with 5,000 variables?
Well, 5,000 variables, the 5,000 variables, it's easy because for that we use this LCD algorithm. And as you can see, it only looks at 3 variables simultaneously. So then we just go through 5,000, choose 3, all the subsets of 3 variables of these 5,000, and we do these tests and we see are the assumptions satisfied for this triple? If yes, we get a prediction. If no, we go on with the next triple, and that we can still run. And then if we go in the FCI algorithm, this is basically the short summary of what the algorithm does. It is also kind of a greedy approach. So it starts with a fully connected graph, and then it looks at every edge and is starting to do tests whether the edge can be removed. And in the worst case, the FCI algorithm is still super slow, NP hard, I guess. But in practice, if your graph is sparse enough, then you can take this greedy approach up to a few hundred variables. And there are also other implementations that are even can be shown to be polynomial time as long as the graph itself is sparse enough.
But how do you decide if something is actually really independent from something that is not? Like, what is your threshold? Like, how do you decide that something is actually relevant from something that is, because it depends on the size of your system, on the size of your data sets. It would depend on how noisy is your system.
So that's a tricky thing indeed. What is often done is you just take a standard conditional independence test, for example, partial correlation test. You pick a fixed threshold and you hope it works.
I see. Okay.
This is one. I mean, the outcome is sometimes pretty dependent on the choice of the threshold. So this is also ongoing research in how can we automate this choice of the threshold, depending on all kinds of things, like indeed the number of samples. One thing is that as your data set grows and grows, you have to, because you want to balance the type 1 and type 2 error of these tests. So it's different from classical testing, where we often only are interested in controlling the type 1 error. Here we want both type 1 and type 2 error to be small. So your threshold has to go to 0 as the number of samples grows in order for the test to be consistent, for example. And at what rate? Well, you can think of heuristics there. Or something else that's actually quite neat is if you use Bayesian tests, then they automatically adapt to the sample size.
I see. But this is heavy, I mean, numerically, I guess.
Not necessarily much heavier than the frequentist tests, interestingly. So, for example, there are versions have been proposed for partial correlation tests, where the p-value can be, the base factor is just a functional transformation of the p-value. So that depends on sample size, for example. So there are some Bayesian methods that are as quick as frequentist tests that I can use.
Thanks. Thank you.
Alexander, you have one more question?
Yeah, if there is time. Yeah. It's a bit more, yeah, it's a bit outside. It would be interesting to use such models, this kind of models, to also try to discover or to explore the discovery of non-causal, acausal law-like correlations, right? So this is because I worked in logics for quantum mechanics, and right, so there you have statistical correlations that are not due to confounders. At least that's what quantum mechanics says, like the common causes, but they are nevertheless systematic and law-like, right? And yeah, you don't want to postulate it, but you want to say, how would I discover such a thing, right, from the data, right? So there is, you can put some background knowledge into the model, like you did already anyway. Things like certain variables are separated by a space-time distance. Sorry.
Sorry, it's lunchtime here, so my little son is bringing lunch.
Maybe I should ask you some other time.
No, sorry, but continue. So you were at
Yeah, so certain variables, the background knowledge separates certain variables by something called space-type distance.
Mhm.
Means they cannot be directly causally
Yes.
interact with each other.
Mhm.
There might be other hidden exogenous variables,
Mhm.
but we try to eliminate them, and we systematically discover a statistical correlation between the
Mhm.
values of those variables, like two coins that are entangled far away from each other, right?
Mhm.
And of course, you can postulate a hidden variable. People did that,
Mhm.
right? That explains both because it's somehow far back in time.
Mhm.
But then you can also try to eliminate that by doing interventions of a kind, like for instance, measuring different bases here and
Mhm.
there, and
Yeah, so
analyzing the correlations. And in the end, okay, modulo some assumptions, for instance, that the interventions are truly free, which is in actually the Pearl model too, the fact that I do the intervention, so and I have free will, because without that, the whole discovery doesn't work.
Mhm.
So because if I have a common confounder that also determines my actions, then bye-bye. Okay,
Mhm.
so assuming that, then you may actually the data might be used to discover such causal laws, right, in the correlations, and that would be an interesting totally different application than what Pearl usually does. For science, for philosophy of science, maybe you'll be interested. Even in day-to-day life, it's not.
So you mean to discover kind of these entanglement?
Yeah, phenomena like entanglement type, right? So when
Yes. Mhm.
doing certain, yeah.
Yeah. So it is. Yes, I completely agree. That's it's not something that I know a lot about or I've worked on a lot, but it's definitely kind of intriguing.
Yeah, philosophically that would be interesting, because in the end, the goal of science is not necessarily to discover causes. Cause is just a special kind of, but to discover laws. And if the laws happen to be acausal somehow, like, or partially causal but not fully, like, then such is life. I mean, you want to discover systematic correlations that are not spurious in the data, like laws.
Yeah, but I'm not entirely sure. So what approach to take, because you can think about quantum mechanics as being a generalization or as being an application of non-commutative probability theory, where you basically say, well, the axioms of probability are wrong and we have to make them non-commutative.
Yeah, that's one approach.
That's one approach. The other approach is, well, we believe in probability theory, but maybe we should look at our causal assumptions better, whether we can still assume that we are influencing the system, we are not influencing the system if we are measuring it or stuff like that. I'm not sure how the two are related, but
no. But you see, when physicists actually do the statistics, because they do statistics on these things, like right, and they actually use probability, the laws of probability, the standard laws of probability when they do the statistics, right? Well, to analyze like to see the so they don't. Yeah, the non-classical probability approach is a kind of theoretical approach to try to make sense of these non-causal laws in a kind of quasi-causal way, like as if it's, but that's a different story. I'm not looking for that. I'm just saying, okay, from the data with interventions, like in a causal model, you do interventions, you observe the statistically what happens. You may try to postulate more endogenous causes, but in the end, there are these no-go theorems that say, well, modulo some assumptions, as in locality, no superluminal effects. There is no explanation based on common causes, right?
Exactly.
So then,
so I'm not entirely sure what exactly you propose, because if I were to use these algorithms that on that data from entangled particles, for example, and I put in the usual background knowledge about the usual background knowledge assumptions, then the data wouldn't fit, right? I mean, it would, for example, start to violate Bell inequalities, whereas you can derive the Bell inequalities within this framework if you put in the assumptions.
Well, you can derive Bell inequalities if you postulate the fact that these variables, that the correlative variables have a common cause.
Yeah.
Right. Then so if you postulate that causal action.
Yeah, but
it essentially means you can reduce to absurd, you can reduce to contradiction a proposed causal effect, a proposed causal explanation. But that's exactly what I'm I'm asking for.
Okay,
like use causal models against causality in certain. I mean, use the type of model that you have to systematically explore possible causes, and in the end, to in some cases be able to conclude that probably there is none. I mean, in the sense that probably there are some effects that are not causal, though they are not spurious either, they are not confounding. And but I mean, I see no reason why in principle this not be doable. Of course, modulo a lot of things, and it will be interesting.
Yes, I agree.
It's just a meta comment. Thank you.
Yes.
Thank you for the talk. Very interesting.
Thank you.
Velimir, do you have a question?
Yes, please. Thank you, Joris. It was very interesting talk. I would have a couple of questions. The first one would be related to this separation criterion. This is for establishing correlations in the graphs, right?
Yes.
And we are using somehow, we use it somehow for causality. I don't see where is, what is the exact meaning of this separation in causal modeling?
Yeah, okay, I can see, I appreciate the question in the sense that it is not easy to see. I'm not sure if I can easily answer it on the spot.
Okay. Maybe through these graphs at the beginning, what is the difference between correlation and causation? On the first graphs, before that, when you introduced here, this graph I introduced.
Yes.
Yeah. So if I understand well, when you do intervention x3, you will remove these two edges between x2 and x3, right?
Yes,
and in this way, what are you doing with causal relationships in this graph?
Yeah, so let's forget about nodes x1, x4, x5 and all their adjacent edges, so only look at x2 and x3. So in the observational setting above, there's this edge from x2 to x3. So this means if we intervene on x2, we will see a change in the distribution of x3 generically. If on the other hand we intervene on x3, there's no directed path to x2 here, no directed edge in that direction. So then x2 is not an effect of x3.
Okay.
So that's what it means. And for the dependencies, I mean, you can get dependencies in many ways, of course, either through a direct causal relation or through indirect causal relations or confoundings, etc. You can even get them through conditioning. So if we condition on x, so suppose that even there, so here in this graph at the top, there's a confounder between x1 and x2. But suppose that it wouldn't be there, then x1 and x2 would be independent, but they become dependent if we condition on x3. And deseparation allows you to quickly read off those things from the graph.
Excuse me just a moment. So if between x1 and x2 we don't have edge, and we observe x3, x1, and x2 becomes dependent. This is the...
If we, so x1 and x2 are independent if that edge is not there. But if we condition on x3, so if you look at the conditional distribution of x1, given x, if you condition on x3, then x1 and x2 become dependent.
Dependent, yes.
And so you can, so the edges, they have both this causal interpretation by construction in a way, and then the Markov property tells you that it also has that they also have something to tell about the independencies of all these variables, and these are basically consequences. The Markov property, the deseparation and the Markov property is a non-trivial consequence of the model on the left. So, oh, sorry. So the model on the left starts with saying, well, we have 4 independent variables, E1, E2, E3, E4. They are all jointly independent. Now I define new variables x1 to x5 in terms of the e's by these 5 equations. What can I then say about the independencies and conditional independencies between all the variables? Well, the Markov property tells you, well, first, if you encode the structure of these equations in a graph like this, then you can use the d-separation to draw conclusions about conditional independencies that from the graph that apply to the distribution that is implied by the equations on the left. So it really connects the two.
Seems to be like weaker than causality. This there might be causal relationships, and the separation criterion will tell us that they are independent, or vice versa.
Well, you have to be careful there. There could be. Let me see. So yes, it's weaker in the sense that not every dependence is due to a causal relation, a direct causal relation. But, well, there's something like Reichenbach's principle of common cause. If you have 2 variables, x1 and x2, say, and if you see that they're dependent, then it means that either x1 causes x2, or x2 causes x1, or there's a latent common cause of both. And this is something you can directly prove with the Markov property using d-separation. Because the d-separation tells you if there were no edge between the two, then they must be independent. So conversely, if they are dependent, then there must be an edge, and it must be one of those 3, or actually a combination of the 3.
And maybe it could be interesting to see if there is some equivalent criterion which goes directly to causality. So a kind of this separation for causality and not for independence. I guess that it is an open question.
Well, it was open. It's an interesting question. We have actually been working on that in my group very recently. And Patrick Foray, he came to a solution where he extends the notion of conditional independence to include non-random variables, and then you can actually also use the same d-separate or a somewhat modified notion of d-separation, such that you also track the causal relations with the Markov property and not only the independent structure. So it's actually pretty. So at that point, you see that the two are actually very related, but there are some small differences. But you see the kind of you start to understand better the close relationships between the causal relations and the conditional independence structure, where you can actually start from just a bunch of equations and some independent sources of randomness that are somehow propagated through these equations. Kind of keeping track of how these different independent components propagate tells you something about the causal relations, but also about the conditional independencies.
And when I'm looking to these graphs and when I'm thinking about this solving the equations immediately, what is coming to my mind is a relation to efficient difference. Because you see here, when you do this intervention on the graph becomes okay, it is still with cycles, but some of the cycles are removed, and it is somehow simpler. My question is, how does the intervention affect the quality of efficient inference through free energy minimization? I don't know, did I ask it well, but if you want to what is if we perform, for example, loopy belief propagation on the first graph and on the second graph, before and after intervention? What would be difference in say convergence of this? How does intervention affects convergence of belief propagation in the graph? It seems like that graph is simpler. Maybe the convergence will be faster, or the free energy approximation will be more correct.
Yeah, but it could also be the other way around. So the cyclic model could have could lead to an easier inference problem. Well, I mean, if it's completely acyclic, of course, then we know that we get exact inference, right?
Yeah, yeah.
But if we remove some of the cycles and leave others intact, actually, the inference problem may become more difficult. So it depends.
Yeah.
You can imagine that you have some very strong feedback loops coupled together, but they kind of cancel each other out.
Yeah, you cancel.
If you break one of them, then
yeah. Nice.
Can happen.
Nice.
And well, actually, this subclass of simple SCMs, there the interactions are guaranteed to be so weak in a way that you don't really run into that problem. So you'll always find a unique solution of the equations, no matter on which subsets you intervene. So in a way, that might answer your question. That within simple SCMs, we try to stay inside that regime where. But it's. I'm not sure if there's a really direct correspondence with convergence behavior of belief propagation, but it is in a way related that also here we are looking at the solutions of fixed point equations, let's say. I mean, we can interpret these equations, these structure equations, if they're cycles, as fixed point equations in a similar way that updating the belief propagation equations on a graph are fixed point equations. So there are probably some relationships there indeed, but it's perhaps not as one-to-one as you suggested in your question.
Okay, thanks. Okay, just a short note. It would be also interesting to think about propagation of causality through the network. Because with belief propagation, we are propagating uncertainty. Can we think about some kind of local computation algorithm which propagates information about causal relationships in network?
Never thought about that. It's an interesting direction perhaps to pursue. I've never thought about something like that.
Yeah, okay.
I've actually done research on loopy belief propagation and on causality a lot, but I never considered that particular question.
Okay. Thank you very much. It was very, very interesting and very informative.
Thank you. You're welcome.
I think there's a lot of questions.
Weren't we originally supposed to stop at 12 or not?
Yeah.
Okay, yes.
But I don't know, Alexander, do you want to stay and chat more with Joris or your?
No. I think I forgot to undo.